A bucket crane consists of a uniform boom of mass capital M equals 201 kilograms and length 59.05 feet that pivots at a point on the bed truck. The boom supports an elevated bucket with a worker inside at the other end of the boom as shown in the figure. The bucket and worker together can be modeled as a point mass of weight 199 pounds located at the end point of the boom. By the way, why are we mixing imperial and British units? For no good reason. This is just a textbook glitch and annoyance that all textbook writers do because they think it makes it more real, but it doesn't. So we're going to have to convert all these things into SI units at the end. And I'm going to do the whole problem without any conversions and then convert them all at once to simplify the math that's going on, or really just the tedium. Suppose that when the boom makes an angle of 65.7 degrees with the horizontal truck bed, the truck crane suddenly loses power, causing the bucket and boom to rotate freely towards the ground. Bad news for the guy. Find the magnitude of the angular acceleration alpha of the system just after the crane loses power. Take the rotation axis to be the point where the boom pivots on the truck bed. Use g as 9.81 meters per second squared for the acceleration due to gravity. And for unit conversions, assume that 1 meter is 3.28 feet and 1 pound is 4.45 newtons. Express your answer to 2 decimal places at least. So, a lot of stupid unit stuff and then important physics going on. What happens, of course, is that the person starts to descend, the whole thing starts to rotate about here, and we're looking for that angular acceleration. Going to go to a different page and simplify the picture and do some calculations. All right, here's a simplified diagram with the 2 weights that are exerting torques on this boom, one of which is coming from the person and bucket, which together I'll call object 0, so they'll have mass M0 because they gave us a combined weight, and that's yanking down this way, but also the weight of the boom itself, which I'll just call M like they do, and so has force Fg, also pulling downward and also exerting a torque. Our ultimate goal is to use the second law, tau net equals I alpha, to get an expression for alpha. To do that, we need to get each of those things. So let's start with the torque. The torque of the object, the boom, is going to be mg times its moment arm. And its moment arm is going to be, well, we extend the line of action. We want this distance, which I'm going to call r perpendicular. We can see that we have a triangle, since the gravity acts at the center of gravity, sort of duh. That's a distance L over 2, but I want this side, so I have that the thing I want over L over 2 is an adjacent over a hypotenuse, so that's going to be a cosine, which means the thing I want is L over 2 cosine theta. So the torque's moment arm is going to be L over 2 cosine theta. And then the torque due to the guy in the bucket and his weight and so on is going to be their weight, m0g, times their moment arm, which will be L times the same factor of cosine theta. We can see they're basically the same kind of triangles. Or put it a different way, they're in similar triangles. So we know we'll get a similar result. On the other hand, the rotational inertia is going to be the sum of the one from the boom plus the one from the person and bucket, because we'll treat them as one object that's rotating. But if an object can be broken into distinct parts and we can get their rotational inertias, we can just add them as long as they're rotating around the same axis. The boom is a stick, and in your textbook somewhere or in our class notes, a stick rotated about one end of the stick has a rotational inertia which is 1/3 ml square. The person and bucket, they say, treat as a point mass, so it's m0 times its distance squared, which is L squared. This lets us put together, back into tau net, we can say, so we go back to this equation, and maybe we should get some space here. We'll get with that tau net is I alpha. So we have mg L over 2 cosine theta plus m0g L cosine theta equals 1/3 ml square plus m0l square times alpha. And then we have to do some algebra. One of the factors of L cancel, and we get something like alpha is, there's a G and an L left over. On this side, we would have, actually, you know what? Let's just write them out. mgl/2 cosine theta plus m0gl cosine theta all over 1/3 ml square plus m0l square, which, let's do it this way. So we can now factor and simplify. Alpha is, let's pull out a g and l and a cosine. So I have g, l, cosine theta. And then what's left over is a half big M plus m0. And then we divide that by, let's factor out an L square. And we have 1/3 big M plus m0. And then we do some cancellations and so on. I guess we can only cancel one thing. We can cancel one factor of L. And we're left with that alpha is g over L cosine theta times an incredibly annoying fraction, which is something like 1/2 the mass of the boom plus the bucket over 1/3 the mass of the boom plus the bucket. And I am pretty confident that that's the actual answer, but it doesn't help us in terms of the problem because we have to go back and get all the stuff in these terms. Looking at the problem, the sapling numbers I was given was that the mass, big M, is 201 kilograms. That's great. And we're given that L is 59.05 feet, which is annoying, but then they say, remember that there is 1 meter per 3.28 feet. So we can get what that means. That turns out to be 18.003 meters. Sure. What else we need? They gave us G. We know what that is. We know, of course, G. They say use 9.81 meter per second square. They give us that theta is 65.7 degrees, so fine with that. And then lastly, we need m0. But m0 is given not, of course, as a mass, because that would make life easy, but as 199. So it's going to be the weight over g. So 199 pounds times what they give us as conversion factor, which is that there are 4.45 newtons per pound, and then I've got to divide by the 9.81 meters per second square to make it into kilograms, because why not? 199 times 4.45 over 9.81 turns out to be 90.270 kilograms. All right, and now I'm going to throw in a calculator and see what we get. According to my calculator, we would end up with an acceleration that is 0.27 meters per second square. And that accords with what Sapling had said, so I guess we're all in agreement.